Log on, tune in, find out. Another good idea from Cambridge.
Give you some examples of application of adaptive design and design of experiments in early stage, and then we'll move in the later. I think Sergey has a mix between early stage and those ranging study. Okay, so quickly, do you have your mic?
Yes. Yeah.
Very good. Yeah. So let me find your. Yes. Please.
Okay. Yeah. Thank you, Vlad, for inviting me. I hope you will not be too disappointed because you just said that I will be presenting a case study, and maybe you thought I would be talking about the project we did together last year. This is completely different. Okay, I will talk about a decision theoretical approach to dose finding. And it has always been a big frustration for me that it's so difficult to sell decision theory to physicians. Somehow this concept of a utility function is just not their way of thinking. But since a few months I don't work in academia anymore, so nobody's paying me for going here and nobody's paying me for doing this work, so I can do whatever I want. And so what I will present here is completely crazy. It bears no resemblance to current practice at all.
But can you be fined?
Sorry?
You are not paid, but can you be fined for very crazy penalized?
Okay. So we are, the clinical setting is a very simple dose finding problem where we have to decide on a dose to administer to patients and the benefit to patients, for example, measured in quality adjusted life years, is a function of the dose level, and also there is a risk of side effects associated with the dose level. Here we assume side effect is a binary thing, so either you have a side effect or you don't. And it doesn't really matter how you formulate the utility function for this approach, but for the purpose of this talk, I've just assumed that it is additive, so that the clinician give us some constant C that tell us how much penalty we get for a side effect measured in benefit units, and that the two are additive, so that the benefit is worth the same regardless of whether you get a side effect or not. Of course, that will not always be the true, but as I said, it doesn't matter if you want a different utility function, you can do that. Okay, so for the purpose of this talk, I will assume that the benefit function is known, and maybe that's a little weird thing to assume for a phase 1 study where we don't know anything about benefit at all, but it may not be so unrealistic because typically we don't learn anything about benefit during the phase 1, so we may as well just fix the benefit function to whatever our prior belief is, and that belief will not change. So the essence is that it is fixed throughout the trial, not that it is really known in the ontological sense. The side effect risk is modeled with a single unknown parameter lambda. So the purpose of the dose escalation study is to identify lambda and thereby identify the optimal dose level. So the way it works is that you start by postulate a prior belief about lambda, then you optimize the dose level to give to the first trial patient based on that belief, and this is the crucial thing that I will explain how to do this. Now, once you have decided the optimal dose level, you give that to the first trial patient and see if he gets a side effect or not. Once you have observed that, you update your belief about lambda, and this cycle continues until the optimal decision will be to halt the dose escalation trial. Okay, so in order to get this running, you need to specify a benefit function. That could be anything for this method to work. It doesn't need to have any any good mathematical properties. It is essential, though, that we have a conjugate prior for the parameter in the side effect function. So we specify that, and we specify the cost of of the side effect and benefit units, and then we go. Based on our prior belief, we see that the dose level that would maximize the utility for the first patient, approximately 1.8. But on the other hand, we also want to conduct an experiment that teaches us something. And if we want to to minimize the entropy of the posterior belief after having conducted the experiment, then we get an optimal dose level of approximately 8, and that is a really horrible conflict of interests between the trial patients and whoever benefits from the trial information. So that has to be resolved. So it would be nice if we could answer this question: how much human suffering is equivalent to 1 bit of information? I can't answer that question. Luc, who gave a talk this morning about penalized optimal designs, can answer it, because he put a coefficient of this that allows him to put the information, or in his case log variance, but that's the same thing, into the utility function. I will propose a different approach. I will suggest that we make a whole ethical invoice of the consequences of administering a candidate dose. We'll have to do this for all candidate doses that we consider, of course. So for a particular candidate dose, X, then we measure the clinical benefit and the side effect risk, the cost associated with that to the trial patient. And then we somehow, and I will return to that shortly, we somehow calculate the impact from the information gained from the experiment on the utility of future clinical trial patients, and multiply that by the number of future patients. Now this is a little bit complicated because it should include both patients that will be enrolled in future phases of this study, phase 2 and phase 3, as well as the remainder of phase 1, as well as the eventual clinical practice patients that benefit from this information when the drug comes on the market. Because it's outside the scope of this talk to try to model phase 2 and phase 3, and there have been several excellent talks about it before me today about phase 2 optimization. I will just assume here that's a very artificial thing, but just to make the things easy to write up the utility function, I will assume that the drug goes because the benefit function is known, so we just need to know about the side effects. We'll assume that the drug simply goes into clinical practice at the end of the dose escalation. Okay, so this is how it. I will here propose a very simple heuristic to that allows us to assess the impact on the utility of future clinical practice patients from the information gained from the experiment to give a certain candidate dose, for example x equals 2, to the first trial patient. And this heuristic will in general not lead to optimal designs, but there is a straightforward generalization that does lead to optimal design. So therefore I will go through this simple heuristic. We say that, okay, we are considering the candidate dose x, and that is according to our prior belief associated with a probability of 0.4 of suffering a side effect. Now, so we are considering the case that the trial patient actually gets the side effects, and we can now find the dose that maximizes the utility and give this dose in clinical practice. Alternatively, the patient with a probability of 0.6 does not suffer a side effect, and then we find a different, higher optimal dose level to put into clinical practice, and the total utility in clinical practice is then the weighted sum of these two utilities. Oops. Okay, so here it is. Here's how this goes. You have to, in order to get this working, you have to specify the benefit function and the side effect costs separately for clinical practice and for the trial patients, and they could very well be different. For example, if the trial is done on terminally ill patients that are not so concerned about long-term side effects, while clinical practice patients may be more healthy patients that also may have alternatives and therefore will not tolerate so severe side effects. And here you see that the dose level that optimizes the utility for clinical practice, that's quite high, similar to the one that optimizes or that minimizes the entropy of the posterior lambda. But now we have both brought them on the same scale, namely in benefit units, so that we can optimize the combined utility. And this is, of course, in practice, there's a problem, of course, with this, because it means that the first trial patients must sacrifice a lot of his utility for the sake of the common good. And I recently read a book called Dark Medicine about the trials against the physicians in Germany that had made trials on a concentration camp inmates during World War II. And what they said, oh, we did the ethical thing, we just maximized utility, we killed a few trial patients and thereby saved hundreds of clinical practice patients. So you should honor me, you shouldn't put me on trial. And of course, this is not the way, this is not something that an ethical committee will be happy with, that kind of argument, because we cannot expect these trial patients to sign an informed consent agreement under those conditions. So what would probably often be reasonable would to say that we optimize this under the constraint that the utility for each individual patient must be positive. So it's not always the case. Healthy volunteers, for example, get a negative utility and they are getting paid for it. But there's still, even a healthy volunteer that is paid, there's limits to how much, how negative a utility we will expose them to. Now, this was just a heuristic assumption that this patient under consideration was the last trial patient, and it then gets into clinical practice immediately. What if we instead make the assumption that the patient under consideration is the penultimate? Well, then the conflicts of interest becomes much less severe. That looks good. It's a little confusing. If we instead assume that the trial patient under consideration is the third last or the fourth last, and it starts climbing up again. So yeah. And hopefully this converges at some point, because if I have to integrate the whole utility function over the whole trial for a duration of much more than 4 patients, then it becomes a computer resource problem. Okay, here I have optimized a short trial for 4 patients, and this, well, it basically works as you would expect, with If the first patient does not suffer side effects, the dose level goes up a little. If it does suffer side effects, it goes down. As you can see here, I've put the clinical practice scale axis on a different scale. So than the trial dose level, because the dose levels will be much lower in clinical practice than the ones that we have used during the escalation phase. And that's of course a problem with robustness to our model misspecification, that we will actually be we will have a lot of experience with high doses. On the basis of that, we will make recommendations for lower doses. You can see if instead of saying looking at the dose levels that we recommend, then look at the side effect risk associated with that dose level, and you can see if the first patient does not suffer a side effect, then okay, the dose level goes up, but it does not go up as much as it would if we use the CRM approach of something like that, because the next dose level we recommend is associated with a lower side effect risk than the first one. And that is sort of intriguing, because it may be related to the observation that these fully adaptive trials, they tend to fluctuate too much, to be too sensitive to the information gained during the trial. Well, this design, which is optimal under the utility definition that I have given, that will be a lot less sensitive to the information gained during the trial. So I'd have to apologize for this misleading label here. It does not refer to the assumed last trial patient heuristic. It refers to the principle of just optimizing the dose for the trial patient himself without having future clinical practice into account. I have tried to say, well, instead of using this very complicated model, you could just simply try to give each patient the dose associated with posterior mean of that which posterior mean side effect risk is equal to some side effect risk, and then you can try that with different target side effect risks, and you can see the best we can get is a utility of 29.1. That is substantially worse than what we can get by optimizing the utility, which is not so strange, because you saw that the side effect risk associated with the dose that we actually administer, that is not fixed. It's not a target risk chasing algorithm. It really varies a lot. Okay, this very simple model I've used here was just this gamma Bernoulli model, and there are a lot of different things that you could consider. One thing that is especially important is that this, compared to what CRM would do, for example, then this algorithm gives very aggressive doses early in the trial. And one problem with that is that well, that may be optimal under the assumption I made that there's a fixed penalty for side effects. But if the side effect risk is very high, that also may mean that there's a substantial risk of extra severe side effects that we really want to avoid. And there are different things, different options how one could tweak the algorithm to be more conservative in the beginning, while at the same time maintaining this rational decision theoretical properties. And the easiest one would simply say that say that there's some instead of a linear risk utility relationship, there is some concave risk utility. That would be a very easy thing to do. But another possibility would be to say, instead of measuring side effects, yes or no, we measure them on a count scale and use a Poisson instead of a Bernoulli. Stopping rule, yeah, okay. The procedure automatically stops if the optimal dose is 0. And if one were to use this method with discrete dose levels, as one in practice often does here, the work I've presented here was obviously based on continuous dose levels, then this stopping rule will be triggered more often, and that is simply because it will trigger as soon as the 0 dose is better than the lower dose. But here what often happens if you have a lot of toxicities is that it will not stop, but it will just be looking for some optimal dose that is very close to 0. But of course, we also wanted to stop when we have enough information, and I thought of one way one will probably have to factor in some financial considerations here. I don't think it's realistic to say that the stopping rule is a purely ethical thing. But if one were to make a purely ethical stopping rule, then one could say that, for example, say in each trial cycle there are 10 patients that would have been eligible for treatment if the drug had been on the market, but as long as the trial goes, only one of the patients will be including. So something we have to add of the extra cost of continuing the trial is the ethical cost of denying these 9 remaining patients treatment. Okay. Yeah. Summary. It's the most important thing is that this utility maximization does not in general is not in general consistent with chasing a particular target side effect. It could very well be optimal to give dose levels associated with different side effect risks depending on how our belief function changes during the trial. Model misspecification is a problem. I have just assumed here that the model is correct, so it's no worry that we will end up for clinical practice or for the next phase of the study recommending a dose that is outside the range of the doses that we have actually tried during the escalation phase. That is something that needs to be looked into. I think it's a useful thing here that you can distinguish between the parameters that relates to the trial patients and to the clinical practice patients, because often, the inclusion criteria for a phase 1 study may be different for a phase 2 study, which again may be different from the inclusion criteria for clinical practice. Yeah, that's it.
Questions?
I have a comment. Since you've reached the notion of toxicity severity, we've dealt with that in a number of ways. And in one case, we had multiple toxicities, qualitatively different, each of them on an ordinal scale.
Yeah.
We elicited severity scores from the physicians
Okay.
in an iterative way, and it worked remarkably well.
Yeah. How do you model that? Because I would propose here model it with a Poisson distribution, but that may not be appropriate.
For a multivariate ordinal, we used that. It was Snowden, I guess, had a paper on it. We were just talking about it the other day. You get a multivariate ordinal distribution by using a multivariate normal for random variables. You know, the thing that Shiv and Greenberg and those people use. Yeah. And so you can get the utilities directly from the physicians who are experienced with the different adverse events. And it might fit into your regime, I think.
Yeah. Okay. Thanks.
Other questions? No? Then thank you again.